Welcome to the deep dive. Today we're tackling industrial assessments. We've waded through quite a bit of material, real audits, research on simulation to get to the core strategies.
Right. Strategies for improving energy efficiency, cutting down waste, making things more reliable, and ultimately boosting industrial competitiveness.
And what struck me from the get-go is this idea that it's not just about shaving a bit off the energy bill.
Exactly. The research really points towards a bigger picture, a shift, really, from just looking at isolated savings to a more holistic system-wide view.
Okay, so this system-wide idea sounds like the key thread here.
Yeah.
Because you look at the sources and it's everything from motors to steam to lighting. What connects it all?
Well, it's seeing the whole operation as like one connected thing. The energy it uses isn't separate from the waste it makes or how reliably the machines run or the production flow or product quality. Even inventory, actually.
So for you listening, why should you care? I mean, whether you're prepping for a business discussion, learning about how factories work, or just plain curious, understanding these links seems pretty crucial.
It really is. It's about finding those significant improvements and cost savings by seeing that whole playing field, not just one corner of it.
Which leads us to, okay, where do we start looking? The sources talk about these most discussed topics in assessments.
Yeah, things like energy audits, naturally, and the work done by industrial assessment centers, plus those U.S. Department of Energy programs, the Challenge program.
Motor challenge, steam challenge.
Air challenge, process heat challenge, right? And then you see specific tips coming up again and again, like replacing drive belts or using synthetic lubricants. Simple things sometimes.
Right, the common stuff. But the research also flags some, let's say, limitations with how traditional energy audits often work. What are the potential blind spots there?
Well, a big one is that they often focus just on energy savings, kind of in isolation. They don't always fully weigh the knock-on effects on production levels or equipment reliability or even the final product quality.
Can you give an example of that, how that narrow focus might, backfire?
Sure. Imagine an auditor suggests swapping in a super energy-efficient motor. Sounds good, right? Less energy used.
Seems like a clear win.
But if they haven't looked at the whole motor system, the power feeding it, the controls, the actual load it's driving well, you might create new issues. Maybe the existing wiring can't handle the startup current, or its operating characteristics just aren't right for that specific machine.
Ah, so it's not just the component, it's the whole chain reaction.
That's the key takeaway. Yeah, you've got to consider the ripple effects across the entire system.
So it's that danger of the component level view the sources mentioned, just looking at one piece, ignoring the rest of the puzzle.
Precisely. And another thing is, this narrow view can mess up the savings projections. An auditor might calculate savings based on today's production.
But what if production ramps up next month or slows down?
Exactly. Those projected energy savings can suddenly look very different. It really underlines the need to step back.
Which brings us back to the system. The research keeps mentioning the motor system. What exactly falls under that umbrella?
Okay, so the motor system, as it's defined, is way more than just the motor. Think of the whole sequence. The power distribution feeding it, the starter controls, the drive system itself, the motor, the coupling, the load, whatever it's turning, and ultimately the whole process that depends on it.
So optimizing isn't just about the motor spec, it's managing that entire chain.
That's it, from the power coming in right through to the work getting done.
And the goal then is what they call motor systems management. What's the main objective?
The core idea is keeping that whole interconnected system running at its best, ready to go. It's about proactively managing all those bits and pieces to prevent failures and make sure they're efficient.
Okay, this is where it gets really interesting for me. Because the sources connect energy, waste, and reliability. They aren't separate buckets.
Not at all. They all feed directly into a company's overall competitiveness. You cut energy use, you cut waste, you make production reliable. That lowers your operating costs and means you can deliver consistently.
And this ties into a specific metric, cost per unit of production. Why is that so revealing?
Because cost per unit gives you that broader view. It's not just energy costs. It pulls in materials, energy, production efficiency, equipment reliability, other overheads.
You can even show hidden costs, right? Like bottlenecks.
Absolutely. And even inventory. Think about it. Storing excess inventory means space, lighting, maybe heating or cooling for that space. That's energy and waste tied up right there.
That makes total sense.
Yeah.
Okay, let's talk about some of the programs designed to help companies take this wider view. Industrial Assessment Centers, or IACs.
Right, IACs. These are usually based at universities. They go into small and medium-sized manufacturers and do these energy waste and productivity audits. And a really key point, they provide recommendations, but the company isn't obligated to implement them.
So it's like getting an objective, expert opinion without a heavy sales pitch.
Exactly. A very valuable resource.
And then those DOE challenge programs we mentioned earlier. Motor, steam, air, process heat.
Yeah, these are specific initiatives from the Department of Energy to push for efficiency gains in those particular systems. They offer support, like workshops, and importantly, software tools.
Like MotorMaster Plus.
MotorMaster Plus for motors, yeah. ASE Master for drives, AirMaster for compressed air. Useful tools to help analyze and manage those systems.
And it's interesting you mentioned the motor challenge evolved. It started just looking at the motor.
And then it expanded to the whole motor system and its management. It reflects that learning curve, realizing that optimizing just one part isn't enough. You need to manage the whole thing.
And the sources emphasize this shouldn't be a one-off project.
No, definitely not. Energy management needs to become part of the ongoing corporate culture, as they put it, just how business is done.
Okay, so with that broader perspective, let's get into some specifics, our research highlights for cutting energy and waste. Compressed air systems, I was genuinely surprised by the inefficiency numbers.
They are quite startling, aren't they? Up to 95% of the energy going into a compressor can just dissipate as heat. 95%.
Wow. So leaks must be incredibly costly.
Hugely. The research really pushes for actively finding and fixing leaks. You can even estimate the cost by monitoring how hard the compressors work when production is down. And getting rid of what they call planned leaks, using compressed air for things like cooling when another method might work.
That can add up too.
Big time. And just making sure you're only running the compressors you actually need for the current demand, the proper staging, they call it.
Okay, what about steam systems? Another massive energy user in many industries.
Oh, yeah. Huge amounts of fuel go into making steam. The Steam Challenge program tackles this. And interestingly, demand for steam is actually forecast to increase in some big sectors, like chemicals and food.
So efficiency there is critical.
Yeah.
What kind of tips did the research offer for boilers?
Things like regularly checking the flue gas that helps optimize the fuel-air mix, managing the temperature of that flue gas, keeping soot buildup under control, managing the boiler blowdown process. These all contribute to better efficiency.
Let's switch gears to something seemingly simpler. Lighting. It's more than just flicking switches, right?
It is, although that's still important. The basic rules. Fluorescence off if a room's empty for 15 minutes. Incandescence always. HID lights if it's over 30 minutes.
But there's more technology involved now, too.
Definitely. Automatic controllers, sensors, and just taking out unnecessary lights, what's called delamping, that can save a surprising amount. And there's even a psychological aspect mentioned.
Really? How so?
Well, visible efforts to save energy on lighting can apparently help foster a wider energy-saving culture throughout the place. And when you do upgrade, say, to efficient tubes, it's not just about saving watts. You still need to make sure you have the right amount of light for the tasks being done, following foot candle standards.
Okay, electric motors. EPAC, the Energy Policy Act of '92, pushed for energy-efficient ones. But the decision isn't always straightforward: upgrade, replace, repair.
No, it involves a payback analysis.
Right.
If you're upgrading an existing setup, you've got labor, maybe modifications, the new motor cost. If you're deciding between repairing an old motor versus buying a new efficient one.
You compare the rewind cost to the new motor cost.
Right. And you have to factor in that rewinding can actually reduce the motor's efficiency, maybe by 1 or 2% each time it's done.
And reliability comes into play, too.
Big time. Newer efficient motors generally run cooler and are more reliable than older standard ones. And a rewound motor might run hotter, potentially shortening its life. So it's a balance of cost and reliability.
Variable frequency drives, VFDs. They come up a lot. How do they save energy, and what are the watchouts?
So VFDs let you change the motor speed to match exactly what's needed by the load. Think pumps or fans where demand changes. Instead of running full tilt all the time, you slow it down when you don't need full output.
And that saves significant energy.
Especially on those variable torque loads, yes. The research shows examples with really substantial annual savings. But, and this is important, they need to be installed correctly. Follow the instructions.
Are there potential downsides? Electrical issues.
There can be. Things like harmonics distortions on the power line that can affect other equipment. And sometimes issues for the motor itself, like bearing currents or problems with the insulation due to the VFD's output waveform. So you need the right kind of motor, often called inverter duty, and proper setup.
Okay, moving on to waste reduction.
Right.
It's not just environmental, it hits the bottom line.
Absolutely. Landfilling costs money. Incineration has its issues. The sources really stress having a proper, structured waste management strategy. First up is knowing what you're generating and how much.
Then you look at technologies or process changes.
Exactly. It needs to be organized. The research mentions principles like know your waste streams, evaluate options, set goals, track progress, keep reviewing it.
And keeping everything running, reliability and maintenance. What different approaches do the research cover?
There's a spectrum. You've got reactive maintenance, basically, fix it when it breaks, often the most expensive in the long run.
Then preventive.
Right. Scheduled maintenance oil changes, filter replacements designed to extend life. Then there's predictive maintenance, using tools like vibration analysis or infrared cameras to spot problems before they cause a failure.
And proactive.
Proactive goes even deeper. It tries to find the root causes of recurring failures and eliminate them. Maybe it's an installation issue or the wrong component type being used. It also covers things like addressing unsafe work habits by staff and ensuring proper training, because human error impacts reliability too.
And poor power quality was mentioned as a factor.
Definitely. Things like a low power factor or voltages being unbalanced between phases or just the voltage being too high or too low. All that can stress equipment and shorten its life.
Let's touch on power factor correction. Sounds technical, but you said it has real benefits.
It does. Think of it like this. Inductive loads, like motors, cause the electrical current to lag behind the voltage. This is inefficient. You're drawing more current than you need for the actual work being done. That's low power factor.
And correcting it helps out.
Improving power factor, usually by adding capacitors, means you draw less current for the same amount of work. This can lower your utility bill, free up capacity in your electrical system, and reduce energy losses in wiring.
Any catches?
You have to size and place the capacitors correctly. Adding too much capacitance or putting it in the wrong spot can cause problems, especially with harmonics, that electrical noise we mentioned. And basic stuff like checking for loose connections with infrared cameras is also key for good power quality.
The research even gets into motor design itself. What are the key things to grasp there?
Well, induction motors are the workhorses, right? They use a massive amount of electricity. Understanding the basics helps how the rotating magnetic field works, this concept of slip.
Slip.
Yeah, it's the small difference in speed between the magnetic field spinning inside the motor and the actual speed of the shaft. You need some slip for the motor to produce torque, but too much slip is just wasted energy turning into heat.
And those NEMA design letters, A, B, C, D.
Right, those classify motors based on their torque characteristics. Design B is the common, general-purpose motor. Design C gives more starting torque, maybe for conveyors. Design D has very high starting torque, but lots of slip, so it's less efficient. Design Z was an early high-efficiency design, but it had some quirks like high starting current. Knowing the right design for the job is important.
And things like insulation class.
Crucial for handling heat and determining lifespan. And knowing about inverter duty features motors built specifically to withstand the stresses of being run by a VFD.
Okay, this is a ton of detail on components and systems, but how do you actually apply all this effectively in a real factory? The research talks about industrial engineering and computer simulation.
This is where it gets really powerful, yeah. Industrial engineering gives you the tools like work measurement, process flow analysis to find the bottlenecks and inefficiencies on the ground.
And simulation.
Computer simulation lets you build a virtual model of your factory or process. Then you can test out changes. What if we install this VFD? What if we change the layout here in the computer before you spend any money or disrupt anything physically?
So it's like a virtual test bed. See the impact on energy, waste, production, reliability without the risk.
Exactly that. Simulation tools can handle really complex interactions, crunch lots of data, let you compare different what-if scenarios. It helps justify the costs by showing potential impacts on things like manpower and operating expenses, and it just lowers the risk of making a change that doesn't work out.
Are there real-world examples of this in the research?
Oh, yeah. Examples of using simulation to model energy improvements, optimize waste streams, redesign production lines, improve reliability. The sources also stress needing good data to build the models, and sometimes overcoming resistance to change within the company. But the time savings compared to traditional brainstorming and trial and error can be huge.
The research backs this up with case studies too, right? Different industries.
Yeah, several. There was one at a confectionery company. They found opportunities with motor efficiency. The whole repair versus replace thing fixing overloaded or underloaded motors, improving steam traps, and generally boosting reliability through better motor applications and maintenance.
And an older power plant.
That one highlighted motor efficiency again, but also stressed using the right design of motor for specific jobs, like Design C for conveyors needing high starting torque. And it had really detailed recommendations for a comprehensive motor maintenance program.
What about the bakery and grain miller projects?
The bakery took that holistic view, linking production improvements with energy and waste. They found energy savings in lighting, insulation, boiler tune-ups, insulating pipes, refrigeration switching to synthetic lubes there, and even reducing heat gain through windows. Plus, they improved production flow by fixing equipment and rearranging things, and quantified the cost of wasted space.
And the grain miller.
That was a two-phase audit. Looked at steam, lighting, compressed air, pump seals. Found huge energy waste from compressed air leaks in packaging. They actually quantified the cost. Same with steam leaks and waste steam. They recommended lighting retrofits, address wastewater issues.
In maintenance.
Yeah, observations on needing predictive maintenance, a proper motor maintenance system, using vibration and infrared analysis. And they did a deep dive on pump seal failures. Turned out they were using the wrong types of seals, issues with cooling water, cavitation, really specific stuff. It shows how detailed these assessments can get.
It really highlights how these seemingly small things, like air leaks or the wrong pump seal, add up to significant costs and problems.
Exactly. That grain miller example, quantifying the cost of those air leaks, thousands of dollars a year just puffing away, it drives home the point.
So all this experience and research leads to what's described as a novel approach to industrial assessments. What's the core of that proposed system?
The main thrust is developing an overall integrated system for continuous improvement, looking at energy, waste, and reliability together, and crucially, using process simulation to really understand how changes in one area impact the others.
So explicitly modeling those interactions.
Yes, seeing how energy-efficient equipment affects reliability, how waste stream changes impact processes, how process optimization affects energy use and product quality, even how inventory control ties in. It proposes a methodology: planning, gathering data, doing the assessment with simulation, and then reporting on those interconnected opportunities.
Okay, so wrapping this up, the big takeaway seems to be moving beyond just chasing individual savings.
Absolutely. Real sustainable improvement comes from understanding and managing the interconnectedness of everything in the operation.
And this holistic approach of bringing together energy, waste, reliability, process optimization, backed by data, maybe using simulation, where does that ultimately lead?
To being more competitive, more efficient, more reliable, more sustainable in the long run.
You know, a key insight for me is how the system thinking isn't just for factories. You can apply it almost anywhere.
That's a great point. Which leads to maybe a final thought for everyone listening. In this world that's so focused on efficiency, on sustainability, how can we as individuals or organizations really adopt this more integrated, forward-looking way of thinking?
What connections are we missing?
Exactly. What overlooked links, maybe in our work, maybe even in our own lives, could unlock some really significant breakthroughs if we just looked at the whole system?
Definitely food for thought. If you are curious and want to explore these ideas, the concepts, the resources we touched on, we really encourage you to dig deeper. Think about how these principles might apply in your own world. Thanks for taking this deep dive with us today.